Hi, welcome to Lesson 18A, the area under a curve. The goal of today's lesson is to calculate the area between functions and the x-axis. So over past math courses, we've found areas and perimeters, of course, but we've been able to find areas and perimeters, I suppose, with shapes that have either straight or circular, like perfectly circular shapes, or lines, I guess, boundaries. So obviously we've, the good old rectangle is something that we've found areas for, and the area formula, of course, would be length times width. We can break this up if we had this width, and suppose, for example, we broke this into unit widths, and this is just convenient that there happens to be 3 there, unit widths of 1, then we could find the area of this length here would be 1 times L. There's 1 length there, and then as I go through the formula, there's another length there and another length here. So the formula for the area is, if we take the 1 times L plus the other times L plus the third 1 times L, etc., all the way to the last 1 times L. If there are W rows, then that would mean, so there's W of these single unit rows, widths, then the area, of course, would be length times W. And that's how we sort of get that area of length times W. So we've done that before. We've done, then if we split this rectangle on the diagonal, we've now formed a triangle. So the area then, if we call this now the base, we change the L to a B, and there's the base, and we change that W to an H. It's the base times the height, but of course it's not the full rectangle anymore, it's half of that, so it's base times height divided by 2. So that would be for the triangle. This, of course, would be for the rectangle. So we've had a lot of those sorts of problems. We've also looked at the trapezoid, whether it's a right or a non-right trapezoid. Would that be called maybe an obtuse trapezoid? Where we have 2 parallel sides that are labeled A and B. We've got some perpendicular distance between them, labeled as H. Then the formula for the area would be A plus B multiplied by H, all divided by 2. Because if we took this trapezoid, if we were to duplicate it, flip it around, and match up these long sides here, these angled sides, then what you would actually end up getting would be a parallelogram. And let me see if I can do this. 2, 4, 6, and there's 2, 4, 6 here. So if we match these like this, something along this line, then here's our second trapezoid, and we can see that it is indeed a parallelogram. There's A, there's B, and the area of a parallelogram is just base times height. In this case, it's A plus B times height. Actually, and if we were to take this little triangle and put it over here, now we've formed a rectangle again. Sorry, up here a rectangle. So of course base times height, and because this A plus B is the base multiplied by the height, and we only want one of those, so that's why we divide by 2. Okay, so that's a little background to some of these area formulas that we've been looking at before. So this is all fine and good when we're talking about rectangles or shapes with straight lines, and this is not going to work out very well, but a circle, and the area, of course, of a circle is pi r squared. Okay, so we've done all those before. Now what we're going to do is we're going to look at another situation of finding the area, and that's where we find the area underneath a curve, between a curve and the x-axis, between certain endpoints. So for this example today, this graph is the graph of y equals x squared plus 1. And we see that it is a parabola. There's been no horizontal translation. This is in vertex form with the translation 1 unit up vertically. There's the vertex at y equals 1 right there. And so we want to now find the area under the curve from 0 to 2. Okay, so here's this area that we're going to be trying to find, and the one thing that you will notice is, even though there's 1, 2, 3 straight lines, or lines, I guess, because mathematically all lines are straight, we have this curve here, and this curve is not a circle, but we still need to find the area under this curve. So how in the world are we going to do that? So think about that for a couple seconds. Maybe pause the video if you wish. How could we make this job a little simpler to find the area underneath it? Okay, so this is a branch of calculus, and we know that calculus depended on limits. So what do you think we could do to find the area under this curve? Okay, so now that you've had a chance to think about that, what some brilliant person did way back when is they thought of, well, instead of just tackling this as this curve, why don't we break this up into 4 columns and find the areas of rectangles. So if we were to use this upper left corner here, if we were to use that, draw the rectangle so that the upper left corner of the rectangle would touch the curve. So we have this rectangle here, and then if we were to continue that, we go to this next place here and we form another rectangle so that the upper left corner of that rectangle is touching the curve. We'll do that a couple more times. So we get the idea that we're forming rectangles here, rectangular strips, and this would stand still for me, and we draw this 4th rectangle that goes like this. Okay, so here we have 1, 2, 3, 4 strips in between 0 and 2. Each strip has a width of W, and each strip has their own individual length. So there's a length of this strip, here's a length of this strip, there's a length of this strip, and there's the length of that strip. Okay, so all the lengths are different. So now in order to find the area under the curve, we'll find the area of each one of these rectangles. So the area under the curve is going to be length times width, so that would be length 1 times width plus length 2 times width plus length 3 times width plus length 4 times width. Okay, now the widths are all the same, so that's fine. So what I might do is I might just bring that to the front. So I have the width times the length 1. Now length 1, notice that this length here stops where the function is. Okay, that matches up with the lower part of the function. So that length is actually the y value of the function at that point. So this is w times x squared plus 1. And then, of course, w times x squared plus 1 plus w times x squared plus 1, etc. Now we're going to simplify this a little bit later on, so don't worry that I haven't factored out that w yet. So we'll get to that. So each of these x squared plus 1s, I should have, actually what I should have done, sorry about this, is I should have said, okay, well this y is x squared plus 1, that's f of x, which is x squared plus 1, and to generalize it completely, I should have made this w times f of x plus w times f of x, etc. Anyways, I skipped over that, I've got x squared plus 1 in each of those. So now what we're going to do is, well, we know the width of each of these because we set it. There's going to be from 0 units to 2 units. We're breaking it up into 4 strips. So each width is going to be 1/2. And if I have enough spacing here, I have to make sure I write this so I have enough room. Okay, so each of those widths is 1/2 unit. Okay, those are all the w's. Now, for this height here, it's x squared plus 1 when x is equal to 0. So here I'm going to put 0 squared plus 1. Okay? This length is going to be x squared plus 1 when x is 1/2. Because when x is 1/2, f of 1/2 is that y value right there. So this is going to be 1/2 squared plus 1. And then I move on to, this is x equals 1 here. So this length 3 of this rectangular strip is the y value of the function when x equals 1. So it would be 1 squared plus 1. Alrighty, close that. And for this last one here, again, we've got, now this is at the length 4. This is when the length 4 is the y value when x equals 3/2. Okay, and so it's the y value of here. The reason why these are all the y values, all these lengths, is just the y value of this function is because we're comparing it to the x-axis, and that of course is where y equals 0. So the distance between here and here is this y value minus this y value, which is 0. And L2 is this y value minus this y value, which is of course 0, so it's that minus 0. So that's why we end up getting all these y values as we calculate here. So when we calculate this all out, we can sum this all up. We get 1/2. 0 squared plus 1 is 1, plus 1/2 multiplied by 1/4 plus 1. So 1/2 squared is 1/4, which is 5/4. Then we got 1/2. 1 squared, which is 1 plus 1. So we got 1/2 times 2 plus 1/2 times, so this is 9/4 plus 1. So that gives us 13/4. Okay, and we add all that up after a couple more steps, and we end up getting 3.75 units squared. So now, notice, of course, and I'm going to modify this notation a little bit for this area. Notice that all of these rectangular strips are below the curve. And notice also that this area that I just got, 3.75, is going to be less than the area under the curve, the true area under the curve, because all these strips are, well, less than all of, like, under the curve there. So the area of this strip plus this plus this plus this is going to be less than the whole area under the curve because there are these empty spaces that we haven't calculated the area for yet. Okay, so this is called the area of the lower, the lower limit, or the lower rectangles. So this is the area of the lower rectangles when we calculate all this. So now what we're going to do is we're going to do exactly the same thing, except we're going to make upper rectangles. And I will use a different color here, and hopefully I won't make a mistake because now I'm using pen.